It's time for fun with math, and today we're going to talk about unit circle trigonometry. But first, let's answer today's question. So we want to find the value of this trigonometric expression on our calculator, sine of 135, and then talk about why we can't use right triangle trigonometry to explain this answer. So take out your calculator. And on your calculator, we're going to find the sine of 135. You may want to hit mode first, though, and make sure you're actually in degree mode. Right now I'm in radian mode, so I have to go over, hit enter on degree mode, and now I'm in degree mode. And so I'm going to hit sine of 135, so sine of 135 degrees, and it's going to spit out an answer. And so there's my answer. 0.70710678112, blah, blah, blah. It goes on forever and ever. And now I want to try to explain why we can't use right triangle trigonometry to explain this answer. So let's try to use right triangle trigonometry to explain this answer. So the idea of a sine of 135, remember it's this SOHCAHTOA. So you have SOHCAHTOA. And you need to make a right triangle that has an angle of 135, and a right triangle, right? So here is a right triangle. You have a right angle right here. But then over here, you have to have an angle of 135 degrees. So 135 degrees is kind of like this probably. But that's a problem, right? So there's 135 degrees. What's the problem with this right triangle? Well, one thing is I put an arrow here. I mean, this always goes to the left, and this always goes up. So these sides are never going to meet. So it's not really a right triangle. Yet, my calculator gives me an answer, 0.70710678112, blah, blah, blah. So the question becomes, how is my calculator computing this? How is it finding this number? Where is it coming from? And the place that it's coming from this unit circle trigonometry, right? In general, it's actually coming from this unit circle. So let me show you the idea. So a while back, when people were working with right triangles, they realized they could generalize this sort of right triangle idea using the unit circle. So the idea of the unit circle is you have your x and y axis here, and what you're going to do is you're going to draw a circle of radius 1. That's why it's called the unit circle. So we draw this circle of radius 1. And so if you want, you can put a 1 here, and put height 1 here, height -1 here, or length -1 here, and height -1 there. And this is the unit circle. This actually has a formula, so if you think about it, the formula of this unit circle is x squared plus y squared is equal to 1. And the reason for that is if you take a point on this, unit circle, right? So here's a point, and you draw a triangle on here. We know the hypotenuse, the radius right here, is supposed to be 1. And then you can label the sides, of course. You have input here, which you're going to call x. And you have output, which of course you're going to call y. And of course this is the right triangle. Right, so that's the height y. And of course it's the right triangle, and we know the Pythagorean Theorem. So right here, this Pythagorean Theorem says that x squared plus y squared is 1 squared, right? A squared plus b squared equals c squared. So that's where that formula comes from. And you can do this with any point on the unit circle. So even a point over here, you can make a right triangle right here. And again, your x squared plus your y squared will equal the hypotenuse, which is 1 squared. So this is the equation for the unit circle. So what we can do then is we can actually use the unit circle to extend our definition of those sort of trigonometric expressions. And the way we do this is actually very simple. What we do is you have a point on the unit circle, and this is the angle theta right here that we're making. So there's theta. We'll call this the cosine of theta. And this, of course, will be the sine of theta. So the inputs are the cosine stuff, and so this is the inputs are the cosine stuff, and then the outputs are the sine stuff. And it's easy to remember because it goes x, y, or cs. It's alphabetical, so it's not hard to figure out. So, for example, let's get in here and try to understand what this sine of 135 degrees, how you actually find that number. So what happens, you can think about this, it's a little bit more complicated with your calculator, but you can kind of think about it in terms of the unit circle. So you draw this unit circle, and if you want to compute the sine of 135 degrees, what you would do is you draw a unit circle. You'd have to count off 135 degrees, right? So you start here, and we'll end over here at 135 degrees. So this is 135 degrees. And if you look at that point on the unit circle, so there'll be a point here on the circle, and it's going to have an input, and it's going to have an output. That output value is actually the sine of 135 degrees. So the output value will actually be 0. And let's look at our calculator here. 707 blah blah blah. Okay, so 707 blah 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 dot dot dot. It keeps going on and on forever. Now the input will be cosine of 135 degrees, which you're actually, it's kind of interesting because when you take the cosine of 135, you'll see they're exactly the same, except the cosine is negative. And of course it's negative. It's going to the left, right? So it's going to be negative 0.707 blah 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 dot dot dot. Right? But that's the idea. So that's how we can extend our sort of right triangle trigonometry using the unit circle. And it's important to note that there still is a right triangle here. You can still make a right triangle out of all this. So even here, that over here there's not a right triangle. If you look on the other side, there's still a right triangle. You can make a right triangle right here. And you can even show that, there's this input, which is the cosine of 135. Ooh, I'm on green. So there's the input, which is the cosine of 135. And then there's that output, which its length is the sine of 135 degrees. And this SOHCAHTOA will still work. So let's talk some more about this. So what is unit circle trigonometry? Hopefully you kind of see the idea. It's just a sort of a way to generalize right triangle trigonometry, so you can take the cosine of sine of whatever angle you want, whether it be between 0 and 90 degrees, like the sine of 45 degrees, or it be bigger, like the sine of 135, or even the sine of like 1,432 degrees. So let's talk a little bit more about this unit circle. So what it actually is, and let's kind of compare the two. Let's compare this sort of idea of reference table versus the unit circle. So real quickly, again, what the unit circle is, it's simply a circle of radius 1. So you have x, y, and we can draw this little unit circle on here. So here's my unit circle. So it has radius 1, 1, 1, negative 1, negative 1. It has this formula, x squared plus y squared equals 1. And the way that we use the unit circle is if you give me a point on this unit circle, so some point on the unit circle, you can make an angle here, get this right triangle. So here's an angle theta. And you get this right triangle with input and output. Right? And the input is actually the cosine of theta. So it goes cosine of theta, comma, and then the output, of course, is the sine of theta. And so that's how we use the unit circle to find the cosine of an angle and the sine of an angle. It's really a type of technology if you think about it. So let's compare and contrast the unit circle to the reference table. And so the reference table we talked about last time, and we talked about filling this out. So the idea is you kind of have to memorize the reference table here. And it's not too hard to fill out. So on top I gave you the degrees. These are reference angles for degrees. And below we'll write radians. So here that's 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. So those are degrees written as in terms of radians. So I usually memorize these, although remember pi is 180 degrees. So you can see 180 divided by 6 is 30, 180 divided by 4 is 45, 180 divided by 3 is 60. Oh, and this is certainly a mistake. That should be 2. Pi over 2, or 180 over 2, is 90. So you can kind of, remember here. Remember, pi radians is equivalent to 180 degrees. And that's radians. sorry, pi radians is equivalent to 180 degrees. And then it's easy to fill out the reference table if you can basically remember that the sine of 0 is 0. So I know where to start counting. So it goes square root 0, square root 1, square root 2, square root 3, and square root 4. And then these are all divided by 2. So divided by 2, divided by 2, divided by 2, divided by 2, and divided by 2. We talked about the reason why this is, and this comes from the sort of using those sort of special triangles, using the geometry of the special triangles, you can show why the sine of 30 degrees is actually 1/2. And now cosine theta is just as easy, you just write it the other way. So it's square root of 4, square root of 3, square root of 2, square root of 1, and then square root of 0. And then, of course, these are all divided by 2 again. Divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. Now, notice I didn't simplify these, but if you want to, you can simplify them. Like square root of 0 divided by 2, of course, is 0. This is equal to 1/2. These two are already simplified. And then this is, of course, 2 over 2, which is 1. And the same thing down here. 0, 1/2. And over here you have 2 over 2, which is 1. And what's really nice about this table is if you write it like this every time, so this is how you memorize it, you basically get the tan of theta for free. All right, so what's the tan of theta? You just did the sine of theta over cosine of theta. So it's just 0 over 1, which is 0. The middle one's easy because it's the same number. This number divided by the same number, that's 1. And the last one's kind of easy because you have 1 divided by 0, which means it's undefined. So that one's undefined. These are the only two that are kind of hard, this one and this one. This one's not too bad. If you take square root of 3 divided by 2 and divide it by 1/2, you multiply by the reciprocals and 2's cancel, so it's going to be root 3. And of course, the same thing's going to happen here, but instead of getting root 3, you're going to get 1 over root 3. And sometimes on this one, you like to rationalize the denominator, so it's like multiply top and bottom by root 3. And so on top, you get root 3, and then on bottom, you just get 3. Right, so that's root 3. And on bottom, we have 3. Okay. So now how can we use the reference table to fill out the unit circle? So students are always asking, do I have to memorize the unit circle? And I always say no. You don't have to memorize the unit circle, but you do have to memorize something. And what you have to know is the reference table. And so to memorize the reference table, basically I know pi is 180 degrees, and that gives me the reference angles. And I know sine of 0 is 0. And then I simply count up with the square root and divide everything by 2 and do the opposite. So I'm really only memorizing a handful of things here. And then I need to use those ideas over here to fill out this unit circle. So let's do this. This is a bit of an exercise, so work with me. First, let's just fill out the degrees. So you have 0 degrees, you have 30 degrees, you have 45 degrees, you have 60 degrees, you have 90 degrees. And then the rest of these, we're just going to add. So let's suppose we start with 45. You have 45, you get 90. You had 45, you get here. 135, if you add 45 again, you get 180. If you add 45 again, you get 215. If you add 45 again, you get 270. Oops, I think I messed up here because when I was adding 45, I got 260. I know that's 270. This one's 225. Right, so that's 225, right? 45 plus 80 is 225. Add 45, 270. Add 45, 315. Then add 45 and you get 360 degrees, so I know I did it right. So, you just basically using your ability to count. And then, wrapping around the circle, sort of your ability to tell time in a way. Let's do it with 30s now. So 0, 30, 60, 90. This will get the rest of them. 120, 150, 180, 210, right? 230, 270. Ooh, I'm off. This is 240. Right, so 240, now 270, then 300, 330, and then 360. All right. So now I filled in all the degrees, and now I have to do the radians. Now we've done this before, but again, it's good practice. Here I have 0, and I put pi over 2 on here. I can count in terms of pi over 2. So 0, pi over 2. If you add another pi over 2, you get a full pi. So that's 2 pi over 2. And then you have another pi over 2, you get 3 pi over 2. So I'm just counting things, 3 pi over 2. And if you get back up here, you get 4 pi over 2. Remember, 4 pi over 2, the 2's cancel, and you get 2 pi. Now pick a different angle. Let's switch colors here. Let's do pi over 2, and let's do this angle, which is right in the middle between 0 and pi over 2. So the idea is you just take pi over 2, and you divide by 2, or you can just multiply it by 1/2, which is really the same thing, and you get pi over 4. So right here, this is pi over 4. This is 2 pi over 4, which means this angle here is 3 pi over 4, which means this angle is 4 pi over 4. Then you go another quarter, so that's 5 pi over 4. Then you go down here, which is 6 pi over 4, which are already filled in at some point. I don't remember when. Oh, I filled it in when I did pi over 2. Right, so 6 pi over 4. So it checks, basically. All right, so that was 6 pi over 4. Then we get 7 pi over 4. And back up here to 8 pi over 4, which is 2 pi, so it checks. So that one worked. And now we do the last of the angles right here. So we want to do this angle right here, which, remember, you can look and say 30 degrees is pi over 6, or again, this is a third of the way between 0 and pi over 2. So if you want to find a third of pi over 2, it's just equal to pi over 6. And so this is 1 pi over 6, so just put pi over 6 here. This is 2 pi over 6, so put 2 pi over 6 here, which we'll reduce in a little bit. Then we have 3 pi over 6, which is pi over 2, so it checks. And then 4 pi over 6, which, yes, of course, reduces, but we'll get that in a bit. 5 pi over 6 here, so we're just counting off basically by pi over 6's. 6 pi over 6 checks. 7 pi over 6. 8 pi over 6, which, yes, will reduce. 9 pi over 6, so it checks. 10 pi over 6. And then finally 11 pi over 6, which brings us back to 12 pi over 6, which is 2 pi, so it checks. And so, of course, we should probably reduce these things. So this was 2 pi over 6, so that's really a pi over 3. And then this one here, this reduces. We divide out by the 2's. The 2's cancel, so you get 2 pi over 3. This one reduces to 4 pi over 3. And of course, this one reduces to 5 pi over 3. And so now we put our angles on there in terms of radians, just simply by counting and using sort of the geometry of this unit circle. All right, so that was kind of old stuff. Now we have some new stuff. We want to label the sort of inputs and outputs, the sort of cosine and sines of these angles. Now remember, this reference table already told you what the outputs should be and the inputs. So here you start with 0. So we have the outputs and the inputs. So let's do the outputs first. So sine of 0 is 0. Sine's an output. And then it goes 1/2. So this is output 1/2. And then we have root 2 over 2. So root 2 over 2 goes here. And then we have root 3 over 2. And then we have a 1. And then we do the same thing with the cosines now, but go the other way. So we start up here at 0. So this is cosine of this. So 0, and we're going to go backwards. This is going to be 1/2. This is going to be root 2 over 2. And I'm just copying these off the table, so I'm going backwards now. Then root 3 over 2. So the input here is root 3 over 2. And then finally, the cosine of 0 is 1, and so you put a 1 here. And once I fill this out, I basically have it. You have to remember, this is the first quadrant, this is the second, third, fourth. So all they're going to be the same numbers, but they're going to differ by a plus or a minus. So here, all the inputs will be negative. So we'll have negatives on these numbers. So negative and negative. And the outputs will be exactly the same. So this will be 0. This will be 1/2. This will be root 2 over 2. And this will be root 3 over 2. Because the heights are exactly the same on either side. So root 3 over 2. And then the inputs, they're exactly the same too. They're just off by the negative. So this will be negative 1/2. This will be negative root 2 over 2. This one will be negative root 3 over 2. And this one will be negative 1. And then we move down into the third quadrant, which again, basically the same. You're going to be off by pluses or minuses, but I guess they're all negative now because you're in the third quadrant. So this will be negative root 3 over 2. As that's negative root 3 over 2. And this will be, instead of positive 1/2, it'll be negative 1/2. This one will be negative root 2 divided by 2. And this one will be negative root 2 divided by 2. This one, which corresponds to this point right here, will still be negative 1/2. And the output, instead of being positive, will be negative. So negative root 3 over 2. And then down here, instead of 0, positive 1, you'll have 0, negative 1. On the right-hand side, the inputs will be positive, but all the outputs are going to be negative, negative, negative. So right here, you'll go over 1/2, and you'll have negative root 3 over 2. Here, corresponds to this point right here, it'll be positive root 2 over 2. That's how far you go over. And then you go down negative root 2 over 2. And then right here, you have root 3 over 2. And the output is negative 1/2. And that's how you fill out the unit circle, not by memory, but by using sort of the geometry, or if you want the logic behind this sort of circle. We're really using the symmetries of the circle, right? Okay, so let's move on to the next thing here. So we talked about what the unit circle is, the reference table versus the unit circle. We want to move on now to evaluating trigonometric expressions using these two different types of technologies. All right, so we want to learn how to use the unit circle, and then we're going to learn how to use the reference table to find things like the sine of 135 degrees. So let's do some examples together. So here we are. And the unit circle is a wonderful little piece of technology to use. It's really easy. You guys like it because it's kind of like reading a table, but it's circular. So if you want to find the cosine of 2 pi over 3, the first thing you need to do is just find the angle 2 pi over 3. So let's find the angle 2 pi over 3. So here's the angle 2 pi over 3 right here. And now the cosine is not the input. It's not the output. It's the input, right? So here is the cosine of negative 2 pi of cosine of 2 pi over 3. And so it's just equal to negative 1/2. It's nice and easy. You just look, find the angle, and then make sure you take the right one, the input, because that's the cosine. Now the sine of 2 pi over 3, that wouldn't be the input, that would be the output. So it's equal to root 3 over 2. And that's how you use the unit circle to find the cosine, sine, or of an angle, basically. All right, let's look at this next one here, because it's a little bit more difficult, but not much, really. You want to find the tan of negative pi over 4. Well, notice we can't find the tan. We can only find the cosine and sine, so you have to rewrite this. So we'll rewrite this as the sine of negative pi over 4 divided by the cosine of negative pi over 4. Because that's what the cosine is. Remember that's what the tan is, right? So remember the tan of theta is equal to the sine of theta divided by the cosine of theta. This is one of our quotient identities we talked about. All right, so what? So how do we find this? Now, it's a little bit harder, but not much. You have negative pi over 4. So instead of going up to pi over 4, you go the opposite way. We go down here. So down here really to 7 pi over 4, which is the same thing as saying the angle negative pi over 4, right? You're just going down here. That's negative pi over 4. And then you have the output on top and the input on the bottom. And so if you look here, here's the output. So we'll put that on top. So you have negative root 2 over 2 divided by positive root 2 over 2. And of course, those cancel to give you just negative 1. And so tan of negative pi over 4 is negative 1. And then finally, let's do this last one, and we'll talk about how we can check our work. So the cosecant of 11 pi over 6, well, remember, I can't really work with cosecants. I got to change them to sines and cosines, because that's what this is giving me. So I rewrite the cosecant. Cosecant of theta is 1 over opposite the letter, so sine of theta. And so that's 11 pi over 6. I need to go and find 11 pi over 6. So where's 11 pi over 6 at? There it is right there. 11 pi over 6, so it's like reading a table. And I want the sine, so I don't want the output. I don't want the input, I want the output, because sine is output stuff. So that's actually equal to 1 divided by negative 1/2. And when you divide by a fraction, you multiply it by the reciprocal, so it's really 1 times negative 2 over 1, which of course is equal to negative 2. And it's really easy to check your work on these. So, suppose you want to check this, cosine of 2 pi over 3 is negative 1/2. We're doing radians right now, so we need to make sure that we're in radians. So hit the radian button. We're in radian mode now, and then you just type in cosine 2 second pi divided by 3. And then hit enter, and it says negative 0.5, which is negative 1/2. So you can check all of these just like that. You can plug in tan of negative pi over 4, let's say it's negative 1. Of course, you don't have a cosecant button on here, so you have to do 1 over sine 11 pi divided by 6 to find that answer. So you guys, students always enjoy using the unit circle. The problem with using the unit circle to evaluate these expressions is that first you need the unit circle. So you don't always have this in a chemistry or physics class at your hand. So we need to develop a way that you can solve the same problem, right, without relying on this technology. Basically, you need to build an easier technology to use, and that's with reference tables. Now, you don't like this way as much, and the reason you don't like this way as much is because you have to work a little bit harder to rebuild just the part of the unit circle that you need. So, how do you do this with reference tables? So again, over here we have our reference table, and let's just fill it out real fast. I'd love to hear for us to fill out. So this is 0, pi over 6, pi over 4, pi over 3. The more times you do this, the more likely you are to remember what these things actually are. Pi over 2. This is root 0, remember. Then goes root 1, root 2, root 3, and then root 4. And of course, these are all divided by 2. So you divide each of these by 2. And then the cosine of theta is exactly the same. You're just going to write it the opposite way. So root 4, root 3, root 2, root 1, and root 0. And these are all divided by 2 also. All right, so every time I fill this out, hopefully you kind of fill it out with me. Otherwise, you won't memorize it, and you'll struggle greatly with trigonometry. Trigonometry, basically you get to get down a couple facts, and once you get those facts down, you just use those. Right? You basically learn a couple tools, and then you can use them. So I'm just filling this in for what they simplified to, but normally I just leave them, but I'm going to fill it out here for you completely. All right, so there's my reference table. So now how do you use the reference table to find the value of these expressions, right? So like, how do you find the cosine of 210 degrees? Now, normally in the unit circle, you look for 210 degrees, and you write down the input. So what we need to do is we need to develop the pieces of the unit circle we need. So I use this little sort of saying, all students take calculus. Right? And this is going to help me a little bit trying to figure out if this is going to be positive or negative. So 210 degrees, where does it fall? Let's draw the angle, because we need to find the reference angle too on this problem. So let's draw the angle. So we start here. Then 210 degrees, this is 90, 180. So 210 must be down here because that's 270. So 210 is somewhere right around here. So that's 210 degrees. And what you notice is you fall in this third quadrant. So you fall in this T quadrant. Right? All students take calculus. And what that means is that if you write T here, it's only the tangent that's going to be positive in this quadrant. Right? Over here, they're all positive. So if you have an angle in this quadrant, the sine, cosine, and tan will be positive. In this quadrant, only the sine is positive. That means the cosine and tan will be negative. In this quadrant, the tan is positive, but the sine and cosine will have to be negative. And over here, only the cosine is positive. The tan and sine are going to be negative. And this really follows right from the unit circle. You know, so if you think about it, the inputs and outputs are positive in this quadrant. That's why they're all positive. You take the sine, cosine, and tan, the inputs and outputs are positive. So those expressions have to be positive. Whereas over here, right, the inputs are actually negative. So the cosines will be negative, but the outputs are positive in this quadrant. So the sine is going to be positive of any angle in this quadrant, but the tan will also be negative. Why? Because it's the sine over the cosine. So you have a negative thing divided by a positive thing. Right, well, it's in this quadrant, so I know only the tan is positive. So when I write this, I know it's going to be a negative cosine of some angle, of that reference angle. So I don't want to use the 210. I want to find the reference angle. So the reference angle, remember, it's the smallest angle it makes with the x-axis. So this was 180 to 210, and so that must be 30 degrees. This is going to be equal to negative cosine of 30 degrees. And so then this is going to be equal to, of course, negative, and I can look up in my table, there's 30, cosine is root 3 over 2. So negative root 3 over 2. All right, let's do this again before you think too much. So let's do the next one. We need to find the sine of 2 pi over 3. So the first thing I can do, I can just draw the angle if you want. So let's just draw the angle. So where's 2 pi over 3 live? Well, pi over 3 is like 60 degrees. So you're doing this twice. So it's like, here's 160, here's 260. So we start here in standard position, and we wind up somewhere over here. And this is supposed to be 2 pi over 3 degrees. Now I can tell you that all students take calculus, so I can tell you whether this is going to be a positive or negative number, right? So all students take calculus. Because it's in this second quadrant, the sine of these angles are positive. So I know it's going to be positive, so it's going to be the sine of, and I have to figure out that reference angle. And the reference angle is the smallest angle it makes with the x-axis, so this angle right here. This was 2 pi over 3. To get to pi, you have to go to an extra pi over 3. So 2 pi over 3 plus pi over 3 is pi, so the reference angle is just pi over 3. And so sine of pi over 3, you come over here, here's pi over 3, and sine is root 3 over 2. And so it's going to be equal to root 3 over 2. So we just developed just the piece of the unit circle we needed, then we could refer back to the reference table to get our answer. And remember, this reference table can live in your mind. It's not too hard to kind of write this down in your head and kind of follow where it sort of goes. All right, let's do the last one now. So now this one is the cotan of 9 pi over 2. And so there are a couple of ways to do this. You can rewrite this in terms of sines and cosines, or you can rewrite it in terms of a tan. I'm going to rewrite it in terms of sines and cosines. So the cotan is the cosine of 9 pi over 2 divided by the sine of 9 pi over 2. And so now what I need to do is I need to find out where 9 pi over 2 actually lives. And so on here I'm going to draw my angle. So always in standard position. Now 9 pi over 2, you can do pi over 2 9 times. So it's like 99 times. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's what it looks like right here. You went around lots of times, right? So you went around all the way, starting here, you went around once, twice, and then right there. So that's your 9 pi over 2. So 9 pi over 2. And then again, we'll write all students take calculus, but it's a little tricky because you're sort of on this sort of boundary line. So all students take calculus. And so you really have a choice. Are you in the first or second quadrant? I always tell you just choose the quadrant that would make the most sense. So I probably would put you in the first quadrant here because you're on the boundary. So what that means is that both of these are positive. The cosine's positive in that quadrant and the sine's positive in that quadrant. So it's going to just be equal to the cosine of an angle divided by the sine of an angle. We got to find that angle, that reference angle. So then we can use our reference table, right? So remember, this is the reference table. Find the reference angle. So the reference angle is the smallest angle you make with the x-axis, which in this case, you go either way, but since we chose this quadrant, we'll go this way, which is pi over 2. So pi over 2, pi over 2. And of course, you look this up in your table. And so cosine of pi over 2, where is it at? It's right here. It's a 1. Right? Oh, I'm sorry. I'm in my wrong place. Here's pi over 2. Cosine of pi over 2 is 0. So here's a 0 on top. Divided by sine of pi over 2, which is a 1. So divided by 1. And 0 divided by 1 is just the number 0. Okay. And again, you can check these again with your calculator to make sure they're right. But the reference table, sometimes students try to avoid learning this process, but it's very important, especially when we start to solve trigonometric equations. When we start to solve trig equations, you're going to have to use the same process. So if we get it down now, this will be a lot easier later on. So it's going to take a little bit of practice, but I'll try to help you guys out in class. So there's one last thing we want to do. There's some other problems to try to help us, with sort of going through this process that we've been doing. So the last example we're going to do, we want to find the exact value of each of the remaining trigonometric, and this shouldn't say functions, this should say expressions. So let's change that to expressions of theta. So what does that mean? That means we're trying to figure out these sort of 6 expressions over here. So we need to find, basically, we need to find what the sine of theta is, the cosine of theta, and the tan of theta, which we actually already know. So tan of theta we know is going to be 4/3. It's given to us. And then sort of their companions over here, so the little reciprocal friends, right? So cosecant of theta, opposite letter of cosine is s, so secant theta, and then the reciprocal of tan is cotan theta. So we need to find each of these. And so how are we going to do this? Well, we're going to use the information given to us. So first we know that the tan of theta is equal to 4/3. So that's going to tell us kind of where theta might live. So remember this idea. All students take calculus. So this is a nice little user interface that tells you when the sine, cosine, or tan are positive or negative. So right here, the tan of the angle is 4/3, which is positive. So what this little piece of information is going to tell me, it tells me that I live in this quadrant, because the tan of angles here are going to be positive, but not this quadrant. Because if you have an angle in this quadrant, the tan is going to be negative. And that's really because of the unit circle, right? The inputs are negative and the outputs are positive. So if you take a positive divided by a negative, it's negative. But the s just means the sign, only sign is positive. But you could be down in this quadrant too, because the tan is positive in this quadrant. But of course over here you can't be in here because only the cosine is positive. So it limits me to now 2 possible quadrants. So which quadrant are you in? Well, with this information, you could be in either of these two. But fortunately, they give you one more piece of information. Here it says the cosine of the angle is less than 0. So that means the cosine of the angle is negative. That means you can't be here. If you have an angle in this quadrant, the cosine has to be positive because that's what this means. All are positive, right? And it's really from the unit circle. So I must be in this quadrant here. So I'm going to draw my theta to make my angle. So in standard position, we start here. And my angle winds up somewhere down here. And I don't know what the angle is, but that's my angle theta. So here's my angle theta. And I know that the tan of theta is 4/3. So what I can do here, I can actually make a little triangle right here. Make a little right triangle right here. And notice that it has an input right here and an output right there. And I actually know what those inputs and outputs are because I know the saying SOHCAHTOA. All right, so let's write this down, SOHCAHTOA. And I can use that saying, SOHCAHTOA, to figure out which side is the opposite, what the opposite side is versus what the adjacent side is. So it's TOA, so it goes opposite over adjacent. So the 4 is the opposite side. So here's the opposite side of the triangle right here, 4. And the adjacent side is 3. The adjacent always lies on the x-axis. Okay, and the opposite is always the y if you want. And so now that I know that's 3 and 4, I can use Pythagorean Theorem to find out what this side is. We'll just call it c. And Pythagorean Theorem says basically 3 squared plus 4 squared, it's a right triangle, should equal c squared. And so 9 plus 16 is equal to c squared. So 25 is equal to c squared. And so 5 is equal to c. So this is equal to 5. Now, of course, it is plus or minus, but the hypotenuse is always positive. Oh, and I made a mistake here. One of the most important things I need to include is that this is not just 3. You went to the left, so it's negative 3. And this is not just 4. You went down, so it's actually negative 4. So the signs are going to matter. So that's really actually very important in this problem. So that's negative 3 and that's negative 4. Now you may say, well, where's the negative here? Well, they're here, but they actually always cancel, so we don't write them. So negative 4 over negative 3, they cancel. So we didn't write them. All right, so finally what? Finally, we can write these down. So the sine of theta is the opposite over the adjacent. So it's a negative 4 over 5. And the cosine of theta is the adjacent over the hypotenuse. So it's negative 3 over 5. And then once we have these, the reciprocals are easy to find because we just flip these. We find the reciprocal. So it's negative 5 over 4. And negative 5 over 3. And this was 4/3, so now it's 3 over 4. And so those are the answers, right? Those are the exact values of our remaining trigonometric expressions. All right, so here's what we did today. So let's just review just for a moment. So we talked a little bit about what is unit circle trigonometry. It's simply going to generalize our right triangle trigonometry. We discussed what the unit circle is, and we compared these two technologies, the reference table and the unit circle. And then how do we use them to evaluate trigonometric expressions? And so remember, yes, the unit circle is nice, but if you don't have the unit circle, you have to develop it. So when we develop it, we just develop enough so that we can use it to solve the problems, and that's basically using the reference table. And that's sort of the idea of working with, unit circle sorts of trigonometry.